KEET TV presents Homework Hotline, the after-school show that fuses learning with fun. Watch local teachers bring the classroom on air and online. This is Homework Hotline.
Hey, I'm Beth Baker, and I teach math, and I work at McKinleyville Middle School in McKinleyville, California.
And I'm Jody Himango. I teach 7th grade science at McKinleyville Middle School.
Yeah, and this happens to be a math day, so typically on any given week, the science teacher leads a lesson and the math teacher tries to keep up. And today we go the other way around, so I'm the math teacher, and I'm going to show what 8th graders are working on. So I brought lots of work samples, and we're going to talk about how patterns and visual learning are a great support for learning algebra in a pretty intuitive way. So the idea is to learn algebra in a way that has lots of practical application or lots of concrete examples behind it.
And work on our spatial reasoning.
We are going to work on our spatial reasoning a little bit. I do want to point out to many of the grumpy and frustrated parents and grandparents out there that there's a reason why we teach math differently today than we have ever taught it in the past. Anybody can pick up a phone and say, hey Siri, what's the solution to 2x minus 4 plus 3x equals 18? And Siri will give the solution and all the steps. We're in a very modern world. So now we need to ask deeper and more interesting questions, because all employers out there are going to expect students to use technology to do the paper and pencil part, and expect them to be good at designing and creating and solving much more interesting or complex problems. So as the world becomes more complex, we need to use technology where it's appropriate and also have more interesting or complex problems. So none of us is probably seeing our children do math the way we were taught math, including me. And it's important. We can't get kids ready for 1982, right? We have to get kids ready for whatever their future is going to be 10 years from now. So I know people get frustrated with math looking all different or weird or new, but that's truly us getting kids in the very best position to handle whatever is coming up in the job market of the future.
And they'll be doing jobs that aren't even invented yet.
Yes, the Bureau of Labor Statistics. If you are a data nerd and you like to just go to a government website and just dig through lists and find out what it is the Bureau of Labor Statistics' fastest growing job sectors is like an amazing thing. So if you're a person who likes to look that stuff up, lots of things in the healthcare profession, and lots of things in math and science and statistics is really a big one too.
Right.
All right, so we're going to talk about a math problem that I'm going to give you right now. And so I'm going to actually ask you just to play around with this pattern for a minute, and I got you some felt tip pens.
All right.
So you're going to look at this pattern, and you're going to use your pens, and I'm going to get the kid thinking out of the way and just let you do it for a second. Would you please look at, so here's case 1, case 2, case 3.
Okay.
And you can start just by counting and making a note of how many squares you see in each case. So why don't you start with that?
Okay, I'm going to borrow your pencil, I think. I like to write in pencil.
Okay, good. Just check the sky cam and make sure people can see it.
So here we have 4. Here we have 9. And there's a bunch of different ways to count this. So you could do 2, 4, 6, add 3. And those are the kinds of math problems we're encouraging kids to do. So I have 1, 2, 4, 6. Add 6 is 12. Add 4 is 16.
Okay. And notice how you went odd, or you went even, odd, even. There's something interesting there too.
Oh, and I also noticed that we could take the square root of these.
So 2 times 2 is 4.
Right.
3 times 3 is 9.
Yep.
Okay, and 4 times 4 is 16.
Right.
Okay.
So that's interesting observation. Maybe.
And by the way, you guys,
I don't know where we're headed.
Is the advanced class, because 8th graders play with this right away. They don't normally hit the idea that they're seeing some sort of squared numbers immediately. So the question here is, how do you see these shapes growing? So the other thing we invite kids to do, and they do this in teams and talk to each other, if you like a top 10 job skills needed for future jobs, usually teamwork and communication are way at the top.
Right.
And math class has great opportunities for teamwork and communication.
Which is also a more modern idea in education.
Absolutely. And so the question is, do you see sort of a growth pattern in here? And could you show it somehow by coloring in where you see the growth?
Yeah, so here's what I see. I think it is part of my spatial reasoning. I see this in the center of each of the structures.
So you see this repeated?
I see that, well, I see this in the middle, and then it's being built upon as you get bigger. So like this is kind of the foundation.
Yeah.
So I color my foundation all in one color?
However it makes sense to you. Some kids do like an arc and then a different color dot, whatever you like.
Okay, I'm going to color these all yellow because I see a certain structure.
And then you see that again.
I see
this is exactly what we're asking
again.
Students to do, is to explain their thinking. And usually, the great thing about teams is you really have to explain. So you're seeing figure 1 repeated in figure 2 and figure 3.
Correct.
Oh, and I'm going to label my figures too. Here we go. Figure 1, figure 2, figure 3. And then we have some extension questions we're going to do in a minute too.
Okay. Up next.
Yep. And so right now I think we've talked about a constant. We see these 4 over and over again. So now if we go to figure 2 or figure 3, how are you looking at the growth? What are you noticing?
Can I color again?
Yes, please. We brought all the colors today.
That seems fun.
Yeah.
And then I think, and that makes it easier for your brain to pick out the pattern. So I see it growing to the top and to the sides.
Yeah. And we're going to put some numbers on our growth in a minute too.
Not my best coloring job.
No. Okay, that's very nice. Okay, and is there any more coloring you'd want to do to complete your thought?
I think I would want to continue my rainbow design. Mostly so it can look cool, but also to show that the structure in my mind is being built in this way, kind of one on top of the other across the whole thing.
Yeah.
And I cheated and I looked at how the students did it, and that's not how they did it.
No, and then I have a way that I don't think they've thought about either, so I have my way, and I'll sort of save that for the end so I don't pollute anybody's
Which is
thinking.
also the cool thing about math is you can arrive at the same answer in different ways.
And this is a classic example, and by the way, if you're interested at this, if you go to ucubed.org, there's a million amazing activities that people who are just into this style of thinking can just do. So it's open source, it's free to everyone. Dr. Bowler is a professor at Stanford, and she's written lots of amazing math books for all different grade levels. And this will get into some pretty nitty-gritty algebra in a little while, but not yet. So the other thing we could do right now is we could say that this one is just a 4, right? This one is the same 4 that we had before plus these orange ones. So that's 5, and we might color code it. And then if we do this 4 and then 4 plus 5, here we go 4 plus 5 plus something for your purples. So if you were to continue this little math problem, you'd go 4 plus 5 and then what for this top row?
Okay, so I'll try to write it in the same area you did. 4 plus 5, and then we have 1, 2, 3, 4, 5, 6, 7.
Okay, good. So the 4 is that little, it's like the seed that your pattern is growing from. And then 5 is where you were looking at the orange ones, right?
Right.
And then 7 is where you're looking at the purples. Yeah. So we should be able to sort of take our thinking apart and explain each part of it. Now, you might have been working with a student who saw it a totally different way.
Right.
Okay. So now, do you understand your pattern enough to tell me what do you think figure 10 would look like? Can you take a big jump?
Can I draw on the paper? Because that's what I would want to do. So figure 10 would have a new box there.
Oh, and we have lots of paper.
A new box here, a new box there, a new box there.
Yep.
A new one there.
Yep.
Here, here, and here.
And then on the end too.
Oh, yep.
There's one more that wants to get in there. Yeah. Okay. And so that would be figure what? So you just added
figure 4.
3. Yeah, so now, so kids can definitely get up to figure 10, but do you see how I've given you a humongous jump?
Yes.
So figure 4 for sure would be whatever the heck this is, and we could just count it.
Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. So figure 4 would be 4 plus 5 plus 7 plus 9.
And by the way, would you notice there's 4 terms in that sentence and it's figure 4?
Okay, so we'd have 10 terms.
Yeah, so the question is there a more efficient way to jump to it?
Well, I'm noticing that after our initial 4, we go up by 2s in the odds.
Yes, absolutely. So you have sequential odd numbers.
Right.
And I do have more paper, so if you want to grow onto another sheet, you can.
Okay.
Okay. So very often what we do is we ask students to begin a simple pattern, and this is called low floor, high ceiling mathematics. So we try and start with an activity that everyone in the class, no matter what their skill level or their background or how math was for them last year, everybody can start it. So the beginning of this problem is just count the squares and say how many there are. And then we start to push, can you extend the pattern? And then we start to push, can you generalize the pattern? And generalize means no matter what figure number I give you, can you figure out how many squares would be in there, even if you haven't drawn it?
Right. I wouldn't want to draw it, because that would take forever.
So figure 10 is going to have a lot of boxes in it.
Right. So, and I'm looking, so if we're looking for patterns, then I'm noticing across the bottom we have 2 squared, 3 squared, 4 squared. So figure 3 is 4 squared. So I would assume figure 10, I would maybe want to pencil and paper it out, but I would assume figure 10 would be 9 squared.
Right, so we'd want to see, so since figure, so
and we would have,
and you want one more than the figure number. So figure 3 goes to a 4.
Gotcha, I went the wrong way. Ooh,
which happens with 10s and 11s.
That's not an awesome eraser.
So the erasers get old and dried up.
Yes.
Yes.
That, yeah.
Yeah.
And depends on the pencil. So we would have 11 squared.
Yeah. Nice. Yep. And then you have these moments. So we have what we call in math an important mistake. And an important mistake is one where once everybody discovers it and talks about it and works through it, everybody has learned a little bit more than they knew before.
Right.
Which is different than an unimportant mistake, which is, for example, when you have a computation error. So if I'm going super fast and I say 5 times 4 is 15, just because my computation was sloppy, that's usually considered to be like an insignificant mistake. There are times in class when a student does something really important, like they get the figure number, they know to adjust it by 1, they apply this concept perfectly, but their adjustment by 1 was down 1 instead of up 1. That's the time when I run around and like give like those safe, respectful, responsible behavior tickets to the whole team for stopping to discuss it, because that's an incredibly important and special moment. And in math, so many people think, oh, I made a mistake, the whole day's over, I should just go home. You know?
Well, I think a lot of people think that in life.
Yeah. So we don't get to, like, you know, there's that thing about you fall down 2 times and you get up 3 times.
Right.
Like in math, that's super important. And also just to kind of work through it, like we're interested in the mathematical discussion that happened. We don't really care that somebody adjusted 1 down instead of 1 up on their figure number. Okay. So that is called like a really interesting mistake where we can have a really wonderful conversation. So usually that's when I'm cheering my teams on, like, you guys are amazing and awesome. And for someone to be brave enough to make a mistake and then figure it out and then move on, that shows tremendous confidence.
Right, and resilience is really important.
Yep, and sometimes that's where you see fantastic leadership skills too. So you'll see a student in a group who's got amazing leadership skills who can moderate the discussion even if they're not in the forefront of the mathematics. And that contribution is just as important.
Absolutely.
To keep everyone involved. So we're going to take this and reel it in a little bit. Okay, so it's, and by the way, when your paper becomes a mess with interesting ideas all over it, that's a wonderful thing. I'd much rather have a paper that's covered with interesting ideas.
Well, and the other thing the other pattern I'm noticing is you could add the numbers.
Yeah, so we're going to do a couple different tables.
Okay.
So we're going to start a T table here, and over here we're just going to talk about the figure number.
Gotcha. Ooh, okay. I love a T table.
And then over here, science teacher. Math and science teachers really doing our thing together here.
Well, and the nice thing about T table is it's a really easy way to organize your thinking so you don't make those mistakes.
Yeah, so or you catch them more easily.
Right, because you're building it from the ground up rather than making big leaps.
And then later on, now the 8th graders whose work I'm going to show in a minute, so I have lots of beautiful 8th grade work to showcase here. So I've got like great stuff that kids did. And they explained. So I would say that your thing that you were thinking was like a rainbow.
Yes.
This is a student who called splitting it up. And they spread the left and right and let things grow up in the middle. And sometimes this is called the volcano method because it's like a volcano putting magma up through the center. So Kalia, Cage, and Gage, this is theirs. And then they wrote a little statement about how they saw the pattern here, is that lots of students saw it lots of different ways. Here's students who saw a mountain. So they saw drops, they saw a mountain getting built. So you can see their little arrows showing that they saw them coming in on one side, on one edge. I don't have any examples, I don't think, that show your rainbow method. These say, we see case 1 rocketing up through each pattern, case 2 and case 3.
Wow.
The other blocks appear from beneath.
Interesting.
So it's getting boosted up from above, and you can see those arrows really help.
The psychology of where you see the pattern being built is interesting.
And also the teams of kids that have to really communicate hard. So what they don't know yet is this is all turning. Oh, and then they did lots of other cases. And then it says surprise on the back. So this one, students were supposed to name their pattern. And so like Math Mountain or splitting it up. But these guys named theirs Dwayne the Rock. So that was the name of their math for the day. So we didn't say that the math had to fit the pattern that they were doing.
And
right?
I'm sure in their minds it does.
Who knows? Yeah. So the other thing that gets really important later on is figure number 0. Because that becomes your y-intercept when you're graphing.
Right.
So that becomes a really significant thing. And so we can talk about how we get there. So typically when I do these tables, I'll go for a while. And then here I'll do a lightning bolt to remind us that we broke the pattern. And then we'll try a 10 and see what happens.
I don't like to break the pattern.
Yeah, breaking, well, and it's so much more efficient. So what computers do, if we want figure number 700, a computer will literally just add everything up down to 700 because computers do what's called iteration. They can just keep going 700 times. But humans need something more efficient. So if we wanted some really big figure number, we would need the shortcut like the general case that you just found.
Right.
Right. And then eventually, for the 8th graders, they don't know this yet, so shh, if you're the McKinleyville 8th grade class, don't look. Just go like this for a minute, because this is like January. Okay, we're not there yet. Is we'll do n, and we'll do the nth case. And then we have like big kid algebra going on there. And then this is the sort of thing that you can plug into Desmos or a graphing calculator and watch the machines build beautiful graphs for you.
Lovely.
Because once you have a t-table, of course you get a graph. Why wouldn't you? Okay, so why don't you take a minute and
That's what they're for.
Fill in the pieces that you know so far.
Okay, so we know that this is the figure number. We know that this is, do you want me to write the number or?
So students have a different approach to this. It's
total number of boxes, okay.
Yeah, total number of boxes, 4.
And then case 2 is total number of boxes. See, I want to do this. 2 squared. Oop.
Oh yeah, get the good eraser.
I love writing in pencil all the time.
Yeah.
You can see why. 3 squared. So we have figure 3 is 16. I want to write 4 there. It's 4 squared. Figure 4 would be 5 squared. So I'm predicting it'd be 25.
Right.
This would be 6 squared. So I'm predicting 36.
Yes. And now can you make the jump even though you don't especially like the jump?
The jump is hard. Well, I made the important mistake, so now I know it's 11 squared.
Yes, wonderful. You get the benefit of that.
And hopefully my computation is good.
It's
121.
Great. Yeah. And now I'm going to talk about the general case right now. 8th graders are not doing this at this point in the year. But here I needed 10 plus 1, 5 plus 1, 4 plus 1, 3 plus 1, 2 plus 1, 1 plus 1. Right, so here n, if we were just going to keep blurting that pattern, what would you put?
So you did.
I just said it out loud. I said 10 plus 1, 5 plus 1,
Gotcha.
4 plus 1.
So my gut instinct was to say n plus 1, but that seemed too easy.
Well, it's n plus 1 is absolutely correct, but then you did something to the number because you did these beautiful extra little thinking notes over here. So what else do you do to complete the pattern?
Squared it.
Ba-bam, baby, there it is. You have now derived the algebraic expression. This is the general case. No matter what figure number we give you, you could now, and if the numbers were really big, you would just plug it into a computer. But now if I asked you for figure 700, which is some whoppingly huge number,
right?
You would just say, oh, that's 701
squared.
So now we have what's called the general case. Then if we want to, we can graph it, which is lovely. And the other thing that's important right now is that we can also talk about, is there a figure 0 in this pattern? And if there is a figure 0, what is it?
Okay, so if n plus 1, wouldn't it be 1?
Okay, so 1 and then 1 squared.
Right?
Uh-huh, yeah.
So
then figure number 0 is?
Now that I know the general rule, I want to write it like this.
Oh, look at this. We got the advanced class people.
Only because
Look at her go.
I have to go through the steps to, otherwise I doubt myself.
Yes.
So that would be 1 squared,
Yeah.
which is 1.
Beautiful. The last way we can check it, and I'm going to squish your 1 in over here just so we can talk about it for a minute, is we can also talk about how the pattern grows. So the original question is, how is this shape growing? So it grew from a 1 to a 4. We can put it out here. So it grew by 3, and then you've already noticed 4 to 9. It grows by 5, 9 to 16. Okay, it grows by 7. And so we can also see that growth pattern from 1 to 4 to 9 to 16 to 25 to 36 is it's always growing by the next consecutive odd number. And this is what computers do super well.
Right.
By the way, if I did a second pattern here, and at this point I would tell 8th graders to put their pencils down and just listen for a minute, okay, is from 3 to 5 is a 2, from 5 to 7 is a 2, this one grows by 9, 7 to 9 is a 2. This thing is called the law of finite differences. If you have to go out 1 jump, 2 jumps to find a consistent pattern, you know the pattern is squaring.
Oh, interesting.
And it's
Learn
not
something new every day.
It's not that these are 2s, it's that they're constant, they're the same.
Right.
If it took 3 jumps to get out to be the same, it would
It'd
be
be
some
cubed.
cubic pattern.
So if we had a graphing calculator or computer graph this for us, this would be a curve.
Yes, and we can do a little bit of that curve right now. I do want to talk about the students' work a little bit.
Okay.
Okay, and then we do have one final thing I'm going to point out here too. I brought scissors and we're going to cut things out in just a minute. Okay, perfect, okay. Oh, do you want to set up a graph real quick and just go 0, 1, 2, 3, 4, 5 along here?
Sure.
Okay, and then while you set up the graph, I'm just going to talk about how kids saw the patterns. Okay, and I don't know if you guys want me just to hold them up. So this is the group that saw it coming up, rocketing up from underneath. Okay, so they did not see rainbow. They saw this pattern getting lifted up with a new one underneath, and then they saw this whole thing getting lifted up with another one underneath. Okay, and this team, by the way, did all the way to case 10, and they put 120, and then they fixed it, made 121, and that's probably what we would call like a not very significant mistake, right? Okay. Oh, and then that one has the surprise on the back. And then...
Which one do you want to use?
I think that one will show better.
Okay.
Yeah.
That's what I figured.
And then will you put your 0 in?
Oh.
At your axis?
Yes.
Okay. And then this is one that I would never have thought of myself, and that's the one that splits it up. So they saw the black ones as springing apart and 2 new ones, a 3 and a 2 going into the middle.
Interesting.
And then they saw where the whole thing split apart, and they did a really nice job color coding so you could really see that in their thinking that these 3 right here stayed constant, and then this little one just kept getting shifted over as they went. So the way that you color code adds a lot of mathematical meaning, and sometimes kids just want to color, which does not. I'm looking for a new one. Oh, you know what? Here I think is a team that was seeing kind of, they didn't describe it the same way you did, but this team also did that up and over, right? So we see the blocks growing by growing out the sides and stacking one on top. Yeah, so that's pretty cool too. So they saw something pretty similar. Okay, so let's do a little bit of graphing, and then I'll talk to you about the last way to tackle pattern problems. I have to see if there's one more I want to see.
Oh, one is called the big breakup.
Yeah, and this one was named LeBron James, and then James is spelt funny because it's an in-joke in this particular class, I think. But if you see this one, they just kept piling it onto the side, right? Okay.
Right.
Yeah, so you just keep stacking and stacking. But again, their color coding really shows what they're thinking about. By the way, you can see this one added 5, and this one added 7. So we're still seeing that +3, +5, +7 thing going on there, too. So it's just showing up in different places. Okay, let's take a minute and graph. Can I drive the pencil for a minute?
Yep.
Okay, good. All right, I'm going to make a y-axis right here. using the pencil. And then if I want to get up to 5, I got to get up to 36.
Correct.
So I think I'll go, let's go 2, 4, 6, 8, 10. We're going to get close.
You have
2,
17
4,
lines to work
6,
with.
8, 20. 2, 4, 6, 8, 30. 2, 4, and then 6 up at the top of the universe.
Whew, just made it.
Okay, so 0 is 1, which is going to be there. Then 1 is 4. Then 3, oh, wait, 2 is 9. 2, 4, 6, 8, 9. And then what we should get in just a minute, if I counted correctly, which I think I did, 3
16.
is 16. 2, 4, 6, 8, 10, 12, 14, 16. Okay, 4 is 25, is that right?
Yep.
22, 4, 25. Is we should start to get this curve shape. It's a little bit hard to see. But we get this parabolic curve is what happens. And so you get this beautiful, anytime something is squared, and then we would say y equals parenthesis n plus 1 squared, like that. Here's one thing that students don't always get told, and it's my favorite thing. We're going to see if we have time for it today. If I can find my last paper that I brought. Here it is. If I was to take this and cut them out like this, and move it, I can actually rebuild every square that I'm talking about. See how you can just move it and make a square? So students don't know oftentimes that they have permission to do that. But if you see a pattern, as long as you're not adding or subtracting any pieces, and the question just says how many, you could just rearrange them. And then the conversations get super interesting. Because if I just move these squares over, I can actually literally make the cube that we're talking about each time here. It's kind of stuck. There we go. So see how I can just cut it out and move it? So you can see where I cut them. And then we can see on each one how they get cut. And then you can actually just build a real life square every time. So anytime you have a pattern problem, if it's just asking you how many, if you want to rearrange them, sometimes it's a really compelling way to show what the heck your thinking is. And then if we have figure 1 is 2 by 2, and figure 2 is 3 by 3,
right,
then you can start to really take a look, and you can actually just move these around like this. So just uncut them. I can't get it to go, but you see where it used to be.
Right.
Right, and then we can just actually make the darn square. So look at that. A lot of times the first time you tell kids they're allowed to do that, they are just like, why didn't you tell me before? This is so much easier. So for some kids, just having the power to know that you can actually just not add or subtract any, but actually just move the pieces in the pattern around, you can make such a strong argument for there. So anyway, this is the joy of modern algebra, where you get the equation, the graph, and the table in a way where you can go back and look at your color coding all the time. So modern algebra, parents and kids, I hope you loved it. Thanks.